So the main question in our mind is how and when do we use which data structure? We actually need to kind of understand how they are created, how they are meant to be used in order for us to either use it as they're meant to be or get creative with it and make our own decisions, right? It's like cooking. You know, a lot of times we follow recipes when cooking, but people who are really good at cooking will say, you know what? When you know how tastes work with each other and how the chemistry of the ingredients work with each other, you are able to make substitutes, even though you're missing some ingredients in order to make a right balance of taste, right? So that's kind of what we want to get into. Okay, I'm going to assume you follow some tutorial, you know how to code, but some of these more advanced logic, you're just missing some details. So we're going to go through what we already understand. We know what variable is, right? Have you thought about how variable is represented in the computer? I think we can view the different data structure as some sort of evolutionary path. And we start with just normal variable. How does this work? I mean, variable is pretty easy to understand, right? We have a name that represents a value, and then we assign a value to the variable. So we have a variable here called username. And then at some point, it'll contain a value called Ezra, right? But then the trick of the variable is that throughout the programming, we have an opportunity to change the value of it. And later, when we are using a variable, we can say, well, understanding that we don't know the exact value of the variable, we're going to have a common behavior that uses this value regardless of what the value is, right? So for example, if I say, hey, I want to print out a sentence saying, hello, variable name username, right? Whatever else is responsible for populating this variable name with some value. It can be Ezra, it can be Tom, it can be Sally, it doesn't matter. And then later when we are printing out the value, it can replace the variable name with the actual value. And then depending on what button has been pressed or what the user has typed in, we are able to come up with a varied responses. That's kind of the variable in a nutshell. And I've talked about this before, so we're not going to dwell on this too long. But here's the thing. There comes a point where you want to work with a list of variables. So instead of accessing variables saying, hey, we want to do variable 1, variable 2, variable 3, I want to be able to say, well, here's a list, a variable called the list, and then I want to do something on each of the items in the list, or I don't have to keep up with where each of them are or what the name of each variable are, right? I could just say, well, list 1, list 2, list 3, that all represents different elements in the variable. Honestly, in programming, and not only game development, just in programming in general, that is a very essential and very important thing to have. So we agree that it's important. So we have our first evolution from a variable, which is an array, also known as a random access array. So what does random access list or random access array mean? Now, before we jump in, I wanted to share this brief message with you. Like you, I am a self-motivated person that loves to learn new skills and seek knowledge for my curiosity. And coincidentally, that drive to keep learning has landed me the kind of career that I love and enjoy. And that's what got me here in the first place. So naturally, it is exciting for me to share this brief message from our today's sponsor, Skillup by Simply Learn. It is a free online learning platform offering self-paced courses with free certificates. It's filled with courses designed by industry experts and content made in partnership with Google, Microsoft, AWS, and Databricks. It's all about helping people like you and me build strong job-ready skills across 500 plus in-demand topics. It's super flexible and accessible anytime and packed with career-boosting content. So if you're looking to build a strong foundational skills and earn free certificates, visit Skillup by Simply Learn by following the link on the screen, or you can click on the link down in the description. The variable is represented on a memory stick, and they all have some sort of address, number representing a slot in the memory. And this is fixed. This is what goes into your computer, right? you install RAM, this is what you get. And different size RAM means there's more slots in it. And when you're programming, the way code works is that simply it refers to the slot on the memory for some value in there. So when we say, hey, variable 1, what we actually have is that name variable 1 is associated with, for example, here, number 0. Whenever a program mentions variable 1, that means this is a spot 0 on the memory. So whenever we're referring to variable 1, get the value in spot 0. Why do we need to know this? Well, we need to know this because we want to understand why the next evolution of data structure from variable is a simple random access array. Instead of making a new name for each of the memory slot, wouldn't it be awesome and simple if we can simply say, get the memory value from variable 1 plus 1, right? Or plus 2 and plus 3. So in this example, let's say variable 1 points to a memory spot called 0, and we have some values here, right? So in order to get to the next one, the next available spot, instead of assigning and creating a new variable with the address 1 or 2 and 3 and so forth, we can simply say, well, give me variable 1, give me the value in the memory for where variable 1 is pointing to, plus 1, and then plus 2, and then plus 3. So you see where this is going. Let's do this. Let's say we created a variable called my list. And then when I assign this to a memory slot, I say, well, this one points to an address called 2. Okay, well, I'm just going to say 2 here like that, right? So this is address number 2. So this one points to this. And so this is my list, and I say, well, as I am incrementing the list, I can access any point in this by simply adding the number of slots to the address, right? I say, well, give me the first element on this list. What do? I just say, give me the value of the address of the variable. So it'll give me this value, which is 0th or first element on this list. And if I say, well, I want to actually get the third element, address itself is a first element. So if I say I want to get the third element, right? You want to do plus what? We want to do from here, we're doing 1, 2, right? If you add 2 to the address, that's what the third element is. So, well, I don't really need to get down to the nitty gritty, but basically what we're saying is my list address plus, the element we want, which is 3, minus 1, would be the address of element that we want on that slot, right? My list is 2, and then we're adding 3, third one, minus 1 is 2, so address number 4. And you can try this for everything, and I'm sure you're smart enough to understand where this can go. So this is considered random access array. And why is it random access? Because conceptually, in order to get any of the slots within the array, within the list, you can do it instantly with just by doing a simple math. Getting the address of that memory slot is a single operation. Operation meaning how many steps it takes. Address of the list plus the slot number minus 1. And in our case, so this is a simple list. But here's a problem. It's not just enough to choose an address and say that is my list and start adding to it. Because what happens if I say, okay, well, I'm going to make a list. This is my list. And then it doesn't have any elements yet. And while I'm operating on this, I need to use variables, right? Because it's programming, which means every time we are assigning a new variable, these slots are being taken. They're being taken over. So by the time I have to add an element to the list, we say, okay, so let's say, well, the first time we have no problem. Let's say we wrote Ezra, and then we were operating. We fill this up, fill this up, fill this up with some other element, and then Bob comes up, and then that needs to be added to the list. Well, we say, give me my list plus 1, which is 3, and I want to add Bob here. Well, guess what? There's already a value in there that's being used. It's not clear yet. There is a chance that the next spot on the memory is already populated. The way we solve this, right, the smart people back in the day of computing, early days of computing, what they decided with this is that, well, in order to create a list, you have to determine a size of the list first. So I would say, okay, well, my list is size 5, for example. Then we say, well, my list is here, 2. And we're going to slot out 1, 2, 3, 4, 5. And these will be locked and say, this is my list. So this right here, this many slots in the memory is plucked out and pre-assigned to be my array of size 5. So now I don't have to worry about running the program and then other variables being used and then using this as part of their value store, right? Because they're like, okay, well, this is the zone that the list has pre-assigned and they're off limits. So I'm just going to use this. This is why when you're creating a array, a simple array in a older generation language, you have to pre-assign the size of the array that you're creating. The downfall is a lot of times you get into a situation during programming where you don't know what the size of the array would be. Ideally, you want this size to grow forever, right? You don't want it to be locked in to some size and then be locked out. And alternatively, if we say, okay, well, we want to contain as many memories or as many value as possible in this array, so we're going to make it like bazillion, 99999999999. But what does that mean? What that means is that you are pre-slotting the array of this many size. And remember, memory is a limited resource, which means if you have a big enough size that you pre-assign, you're limiting your RAM usage. This was especially important because back in the day, we didn't have like gigabytes of memory. We had like megabytes, right? And it still is a problem right now. But basically, essentially, that is the issue. You can't just make it huge, but also you can't just make it small because you need to make it appropriate for your size. So ideally, what you want to do is that you want to have a type of array that can grow in size. So the next evolution happened. I mean, this is kind of like the Pokemon Pokedex, and this is like one method of developing. We say, well, from the array came the evolution of array list. I mean, this is kind of an evolution because it's still using the array, but this is a type of array where it is more flexible, right? It's like array plus. So how do we resolve a size changing issue? Well, what we can do is first have a array, right? That's pointing to 2 and say it's size 2. And when they fill up, wherever I'm available, slot out another array of size that is bigger. For example, here I'm going to double it and say, well, this is the array now. And after assigning it, what do? We just copy this value over to the new slot. Now we have a new array of size 4 with the same value, but we are moving the spot completely. And this can be pretty complicated because look at what you need to do in order to fulfill this. This is where understanding data structure becomes really important. And because data structure and algorithm is all about number of operations. And this is where we start to see that kind of come to fruition. Conceptually, when we're looking at it, saying, hey, we're going to make a new array of bigger size and copying over the values, it seems like it should be a simple task. But you have to always think about how slow is it if it is actually really big? Let's take a look at this as an example. For array of size 2, and when we're about to insert the third element, slot out a memory, right? So that's one operation. We got to say create new spot with size 4, right? So we created one. And then we have to go through each element, right? So we're going to look at each element in array and paste to new spot, right? Each element meaning we look at this, that's one operation. Looking at it as one operation. And then we got to paste it to the new spot, which is another operation. And then we got to do it for every element in the array. So here we're doing 2 copies, right? We're doing 2 copies. So this itself right now with just 2 elements is already what? Copy 1, copy 2, assign a new slot, and then, maybe copy over a new pointer, say array is now over here. So that's already 5 operations. We're doing 5-step execution on this. And generally speaking, the assignment of the new slot, creating of the new slot, those are just like constant thing, meaning no matter how big the size of the array is, it's only 2 operations always. So we don't care about that as much, but we want to care about how much slower this operation becomes if the array was really big. And this kind of depends on the number of elements in the array, right? So this is what we would call a n operation. Growing the array, copying the values of the array is an n operation task because what? Because it takes n number of steps, where n is the size of the array. Because bigger the array becomes, you add constantly one more operation to the task. And, in our community, the computer science, we call that the big O notation. I don't think O stands for operation. I'm not really sure what the O in the big O stands for. We would notate this like this, right? Big O of n, indicating this task of growing the array depends on how big the array is. Not very efficient, but it's doable. If it becomes like 10,000 elements, then you're waiting quite a bit. We can really get down to the nitty-gritty of it, but we don't have to do that right now because that's basically a lesson for another day. I don't even know if I will ever talk about that because it's not really relevant to what we're doing. But yeah, it's interesting. It's interesting. So this whole resizing thing is annoying to do, right? Every time something comes into the array, I have to now manage assigning the new slot and then copying over the values and then pointing the variable name to the right spot on the memory. It's annoying. It's annoying to do every time. So people started to come up with like general solution to have this be done automatically. So instead of using traditional array to do it, they made a wrapper around the array saying, hey, well, you know what? We're going to do this anyways every time. So instead of using array directly, let's create a kind of functional structure that does things automatically for us, where it assigns things and grows automatically, called array list. At least this is what it's called in Java. But basically, this one has a function or method called add, right? And whenever you call this, essentially underneath it, it is just regular random access array. And when this fills up, it does the operation of creating a bigger array and copying over the values. So for the most part, accessing the value or inserting a value, right? Accessing or inserting the value is a single operation task in an array, right? Because if you have an array, getting a 3rd, 4th, 5th slot address to either retrieve or put in the value can be done within single operation. In short, it's really fast to use. But every now and then, when you're adding, it does this operation that takes n amount of time. All right, so that's a kind of like minor evolution. Now, some people are like, you know what? We don't actually need to do all of this? We don't actually need to do this because it seems like a weird hassle. Let's say you have a situation where you're adding a lot to the list always, but then you're not retrieving the value as much. So the speed at which you're retrieving the value is not as important. It's just that it sucks that every time you add, you have a risk of running this huge operational load, right? Especially if your array is already million items long. For example, I mean, when it gets to 1,000,000 items long, you have other issues, but let's say theoretically that's the issue. So what if we want to prioritize making that increments, making that adding elements be better? Well, that's where the next branch of evolution came in. This evolution happens from the variable, but I think concept of list is evolving. So this evolution is like adding a sunstone to a Pokemon to do something, right? So this is a, I suppose, add priority. And what do we get? If you already know this, this should probably tell you what this is. Well, we have a memory spot with names 1, 2, 3, 4, 5. And let's say we say, okay, well, this time my list starts at 0, right? So this is our starting point. But instead of saying that the next one is the next element, we just grab whatever spot is available on the memory. So let's say, okay, well, list, your address right now is 0. But some other operation happens where this gets all filled up, and next available spot is number 5. Well, if we're adding to this list, what we can do is instead of resizing, removing it over, blah, 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 we can just go ahead and say, you know what, 5 is available. So let's say this is the next one. And then over here at 0 address, write some information about where the next one is. So we'll say, hey, next is at number 5. So essentially something like this, right? And then when we add another, we have another operation, blah, blah, blah. And then let's say we're at 10 here and say, okay, well, we're going to add another item again here. Then the 5 will say, well, next item is at 10. So what do we have here? We have a list of linked memory spots, right? So 0 is telling you, oh, go to 5 next. And then 5 is telling you, go to 10 next. So in order to add to the list, all you have to do is get the end of the list spot and then put a pointer to the next spot. And we don't have to worry about resizing it at all, because this, you can see that the size of the list can grow infinitely without having to restructure anything. So I would say this takes one operation, a constant time operation, to add, very quick, forever, all the time. You don't have to resize it, so you don't have to do resizing operation, and you can keep growing it. But what is the issue with this one? And this, every data structure comes with pros and cons, right? And that's the kind of trade-off that you learn to love and use. So this is called, by the way, linked list, because obviously this is a list of linked elements. So let's say we want to get a third element. Before, we could simply go, hey, you know what? List plus 3. That's our third element, right? But now we have to go, okay, well, list starts here. We're going to see where it is. We're going to go there, and then we're going to see where it is. We're going to go there. We're going to see where it is, and then we're going to go there. And then only after the 3 hops, you are able to get to the third spot on the array. So if the list is huge and you have to get an element at a certain spot, you have to go through every single element that already exists in this linked list in order to get to the spot, which seems very, very, very slow. And this is why, you know, this whole prioritization of like, okay, well, if you're adding for the most part, then use linked lists. But if you're accessing a spot, you need to access those spots really quickly all the time, then probably just use regular array. Now, some alternative solution to this situation is that, you know, if you are in a situation where you can switch modes, right? Where for half of the operation, you're just adding and adding and adding. And then other half, you're thinking about accessing it very quickly, you could always start with linked list, add to it, and then copy it over, which will be an operation, because it takes that many steps to copy. Go through each element and copy it to a regular array. Now you have the set size already known, and you just copy it to the random access memory, a random access array, and then use that as a retrieval. So same thing, you're doing a little trade-off. Before you were accessing very quickly, but whenever you're adding, you had an operation of occasionally having n number of operation. Now you're being able to add infinitely, but then when you're accessing it as batch, so you do one-time operation of n number operation to copy it over to something that makes it easier to access, right? So we already have a case of using both the linked list, which is really good at adding, and then copying it over to a regular array, which is really good at retrieving to do data retrieval. So we can say, okay, this is used for add, copy, and then this is used for retrieval. Oh, so easy, right? So that's one case of having various data structure for different reasons, and why understanding this would help you make this decision. So the next evolution, and it's more of a behavioral evolution, is called queue or and stack. And this is probably what I would describe this as, right? And the concept of queue and stack is simple. So queue is a line, right? So if you have people lined up, let's say there's a little pizza stand, for example. Yay, get some pizza. I had pizza for breakfast/lunch today, so that's probably why this is in my mind. How does this work? You know exactly how this works. Whoever's in the front lined up first. And then guess what? They get served first. So we say, hey, if you lined up first in, you get to go out first out. So in this list, whenever people or elements get added, they get added to the end of the line. And when we're accessing a value, we are always accessing from the front. If you have a list, doesn't matter how it's implemented, either it's linked list or array, what you're keeping track of is where the top or head is and where the tail or the last element is, right? In this array model, it's important because if you have a head address that's directly here and tail address directly here, we can simply say, hey, tail is now +1, meaning we're just moving it down 1 and then queuing new people in there. And some of the method name for putting it in the queue is called enqueue, commonly. And then putting it out is called dequeue. So when you're dequeuing from a queue, you're taking people out from the front. When you're enqueuing in the queue, you're putting people in the back. And there are a lot of other things you can use this for, especially when you're doing graph traversal. But basically what is important about queue is this. First in, first out. We call FIFO in the industry. What about stacks? Stacks kind of opposite, right? Stack is like trays that are being stacked on top of each other. When you're putting the elements in, we're putting it on top of what's already there. But when you're taking it out from the top as well. So what happens here? So this one came in first, and this one came in last. What goes out first? The last one goes out first, right? So this is considered last in, right? If an element came in last, it goes out first. It's kind of unfair, but it makes sense. And there are cases where this makes sense. Popular use cases for stack is call stack, right? Or if you're a Magic player, Magic the Gathering player, you would call that the cast stack, right? The spell stack. Basically, when I cast or use something, and then somebody uses something else in response, the new one takes precedence, right? New one takes priority because that's the most recently activated card. And if I activate another card, Another card is implemented. So whatever is most recently, so instead of last, we can also replace this word as recent in, first out, so that we can go down the stack one at a time. So those are some concepts there. Cool. So we have been talking about this concept based on how fast it is to add items to it, and then how fast it is to access items from it, right? So all these things happen because of that. But there is something that is very, very important that we haven't talked about. That is finding an item. Let's take a look at this, because this is a very common use case, right? We have some address number that is 0 through n. Well, let's call it 10 because some people like it more specific. And we know the address is number, so it's really easy to say, well, 3rd spot, 4th spot, 5th spot, all those things. But what if we have number of items and then there's a name called Ezra in here, which is my name, and I say, okay, you know what? From the array, find the name called Ezra from this list. How would you do this? How would you implement this? Knowing what you know. I don't know about you, but there's really no clever way to do this, right? You just need to go through each element, checking the value until I find Ezra. So finding operation in this data structure, linked list, array, queue, stack, doesn't matter, requires, at the worst case scenario, because worst case scenario, Ezra is at the end. Worst case scenario, it takes n number of checks, right? N being the size of the array. You have to go through n number of items, potentially, before finding the item you want. So this would be O of n for finding it. So smart people back in the day in computing world was like, okay, well, like, can we make this better? And they said, you know what? We might be able to make this better. And that's when we came up with something called hash map. Hash map is often known as, I think, conceptually dictionary in some places, map on some places. Hash set is also the kind of same concept, but essentially anytime you see mapping, hashing, that just means we're hashing the value to translate it to some number. Let's say we have some value, right? It doesn't matter if it is number, it is string, it doesn't matter. And let's say we can translate that into some code that is a number. Then we say, well, you know what? We're just gonna pretend that that's a slot number, and we'll call that an index number. We can pretend that this code is a slot number and then just directly put it in here. Code number here, right? When I go Ezra and then I translate this value, whatever that method is, and that doesn't have to be defined, it becomes 5, for example. Then I say, okay, it's at 5. And later when I go, okay, well, like, does Ezra exist? Can you find me Ezra? And I'll just simply go, well, Ezra is 5 and 5 is populated, so yes. I mean, it's more like this, actually. It'll go, Ezra is at number 5, and it'll say, oh, it's at 5. It'll check the value at 5, and it's Ezra, so it'll say, yeah, you have it. It's right there. This, seems like a perfect solution because getting stuff is super quick. Imagine how fast it is to put stuff in here. Because all you have to do is translate the value into a number and then slot it in. Perfect, right? And that's how any type of key value pair works. So we can say, hey, this is the key. And we take the value, we translate it into some number, and then that we will slot in the value for that. And obviously there are a lot more nuance to it, but we can talk about that later. Conceptually, this is basically what that is. And the advantage to this, once again, is it's super fast to find things, super fast to insert things, and then even getting things could be pretty quick, right? We still have the same issue, but that's for you to decide. I think we have to talk about this some other time. This can go really long if we're not careful here. We just kind of want to touch on the concept and understand enough to know when and when to not use it. So that's why most of the time we say, well, you know what? Hash key, hash set, map, dictionary is so quick to use, so quick to access, so quick to find things. Might as well use it for everything. That's not always the case because there is a concept of collision. Because we're translating it to some code, something that's not a number into a number, there are cases where different values could result in same code, depending on what the translation logic is. And you can be really good with the logic. You still have to worry about the fact that, let's say, underlying array, the underlying array that I create is size 10. And then some code became 15. What does that mean? What that means is that actually we wrap around. So instead of 15, because there's no 15th spot, I would go, you know what? Let's imagine that we wrapped around once. So we'll put it at code 5, right? Because 10, 15, which happens to be same as the code for Ezra, which means there's a collision. So whenever there's a collision, we have to go, okay, well, let's see, next spot. Well, next spot is available, so now we're going to put Tom here. So anytime I try to access Tom, it'll be like, oh, is number 5 Tom? Nope. Go to the next one, is 6 Tom? Yes. So there's like kind of like ambiguous, hard to tell how long it would take problem depending on how good the coding, the hash coding logic is, right? And so the collision really determines how efficient this is. And so we use some really good way to spread everything out so that there is as little collision as possible. Or you can reduce the chance of collision by making the base level array implements this hash map to be huge, because there's less likelihood of colliding. So in this example, 10, 5 and 15 wouldn't collide, right? And then we wouldn't have to worry about this. So that's what this is. So we have the find evolution, which is another conceptual evolution here. Find. We have what we call essentially hash. Set would be if you're just satisfying it with just collection. It's a set, right? Because it's a set of values. If you're saying, well, for each of the keys we have attached a value, then it's a mapping, right? But conceptually, they're the same thing. The fact that it has word hash in it means that it's hashing, creating a hash code for the value that you're inserting. You're keying it with. So yeah, so this is kind of the basics of data structure. I know we talked about a lot of things today. It's pretty complicated sometimes, but I try my best to explain this. And this is really important. And I think the biggest takeaway is that there are reasons why we have different data structures. And hopefully, if not completely, that I helped today, enlighten some of you guys to understand better what the context of these data structures are. And understanding this would start to make you think, okay, well, I'm trying to find things, I'm trying to access things, or I'm trying to add things. You'll be able to decide what to use when. And you know what? Another fun exercise is trying to create all these different data structure, array list, linked list, queue, stack, hash map, using just regular array only instead of using all these other stuff. And that could be a fun exercise. That might be an interview question sometimes in the future. I hope this was fun. I don't know if it's helpful. In modern computing world and time, it's not really necessary to know all of this, but it is fun to know. It is fun to know. I have a few things in mind I wanted to do. Just like this, I know we talked about memories and stuff like that. I think we can talk about actually how computing works, like CPU operation and what CPU is. And you got a little bit of glimpse of that by me talking about what memory is in computing and how variables work. But there's more to it, right? There's like a bus, there's a clock cycle. CPUs have instructions. How does this instruction work? And that's something that I wanted to touch on. So I'll look forward to that. If you have any other questions, any other concept that you find very difficult to understand that you want to know, make sure you leave it in the comments so I can make a series on that. All right. Thanks for watching, and I'll see you next time.